Hi, everyone. I'm really happy today to have Max Raginsky from Illinois, but now reporting live from Atlanta. And he's going to talk about information-theoretic lower bounds for distributed function computation.
Okay. Thanks, Salim, for inviting me to do this. And I'm sorry it took me so long to finally arrange the date for this. But you know, it's a really fun and cool thing, the Shannon channel. And given the name, the Shannon channel, I hope you'll all forgive me for giving a talk about something that was published a few years ago. It's a joint work with my former student Aolin Xu, who is now at Qualcomm, and it's also about not about neural nets. So again, you know, it's the Shannon channel. We're supposed to be talking about Shannon adjacent things. All right. Okay, so here it is.
With computer audio.
My computer audio.
I don't know.
Why not the TV audio? The TV audio works, right? Yeah. Make it the TV video.
Everybody hear me? And
Yes.
Yes. Okay. All right. So here we are. This is about information-theoretic lower bounds for distributed function computation. So distributed function. Yes,
we cannot see your slides at this point.
You cannot see my slides. Oh, I didn't start sharing. Okay, let me.
Yeah, now we see them, but then I think when you make it full screen.
I think I know what's happening here. Hold on a second. New share. Okay. You can see them now, right?
Yeah, now we can see them.
What about now?
Now we cannot.
No.
Oh, this is the, okay, so this is the anomaly of Zoom. Here's what we're gonna do.
Maybe if you try the full screen, would that work?
Oh, not presentation. Okay.
Yeah, maybe, I don't know.
Yeah, that's what's okay.
Yeah.
Okay, it's an annoying feature of Zoom, I guess. It wants you to share a particular window. All right, we can do it this way. All right, sorry about the technical ineptitude on my part. Let me start my timer. All right, so this is a talk about distributed function computation. So it's a problem that has been studied for quite some time, right? And the basic setting is this. We have a collection of nodes. They're connected in some way by noisy or noiseless channels, but their interaction is somehow limited. And the idea is that each node in this large network has a random observation, and all the nodes want to compute a given function of all the observations. And it's a distributed problem because each node can only communicate with her neighbors. And again, taking into account communication restrictions and related things, there are going to be limitations on how well this function can be computed, whether it's time, error, energy, etc. And here we're going to assume the communication takes place over finite capacity point-to-point channels, and the computation of the nodes is error-free. So the effect of computation at the nodes is considered negligible, and we're looking at the impact of essentially the fact that the channels are capacity limited, and the fact that each node has a private observation and therefore has a lot of uncertainty about the value of the function initially before the process starts. So our goal is to characterize fundamental limits of distributed function computation, taking into account constraints on communication and also statistical uncertainty. So let's first kind of give our dues to related work in computer science, starting with the groundbreaking work of Yao from the 1970s. There's a lot of work on communication complexity, which is mostly combinatorial and essentially counts bits that are exchanged among the nodes in some constraint scenario. Later on, beautiful paper by Rajagopalan and Schulman in 1984 looked at distributed computing as a coding problem. in the error correction coding sense, and provided fundamental asymptotic limits on distributed computation. So how much overhead you need in order to simulate some noiseless protocol for computing a given function over a network. So you start with the existence of a given protocol that works for the noiseless network and is in some sense optimal, and then you essentially kind of mimic these ideas from, let's say, Boolean circuits with unreliable gates in order to introduce enough redundancy to pull it off. In the information theory literature, the paper by Orlitsky and Roshan 2001 looked at computing a function as a coding problem. It's kind of a functional compression problem where you have nodes and each of them has a stream of values from a random source. Let's say IID realizations of some pairs, and all the nodes want to compute the functions of these pairs, right? So the idea is that it will look at the sort of block length effects. Even more recently than that, there was a paper by Ayaso et al., where this problem of distributed computation in noisy networks was taken up and considered from an information-theoretic point of view, taking into account capacities of channels and things like that. So we're going to build and extend this work and improve on some of their bounds. All right, so here's the setup. We're going to represent our network as a directed graph, right? So the vertices represent nodes, and communication takes place along directed edges, right? So if nodes U and V are connected by an edge that starts at U and ends at V, then node U can send messages to node V. And therefore, each edge, these are directed edges, so ordered pairs of nodes. Each edge is associated with a channel, which we're going to denote by KV, KE rather. So the nodes, the edges label the channels. And we view channels as transformations, right? So we have an alphabet corresponding to communication from node U to node V, and an input symbol from that alphabet gets mapped to a probability distribution over output symbols. Right, it's standard kind of a thing, and we start with local observations. So there are some functions, there are some variables, random variables W indexed by nodes. So the vector of those variables is distributed according to some probability measure, and each node only gets the component of that vector corresponding to its label. Right, so the idea is that node V only gets to see W sub V, and the problem is, compute a given function, f of W, so this vector of all the random variables, through local communication, so communication along directed edges, and local computation. We assume that the function f is known to everyone, and the prior distribution of this random vector W is known to everyone as well. Right, so that's the setup. And then, of course, we want to formalize the notion of a distributed computation algorithm, mostly for essentially bookkeeping, right? So again, the problem is, given this directed graph representing the network, given the description of all the channels corresponding to all the directed edges, we wish to compute a given function, f, of the initial observations W, and we denote the value of f at W by Z. The computation is to proceed via local communication and computation. So A is a generic T-round algorithm, and the algorithm will consist of encoders, by means of which each node at each time step sends messages to its neighbors, the nodes that are sitting at the outgoing edges emanating from that node. And each node, once this is completed for T rounds, will apply an estimator. The estimator will take whatever this node has and produce an estimate of the function value for that node. So the idea is that at each time T, ranging from 1 to capital T, each node computes an outgoing message. So this outgoing message is meant for all of the nodes that receive messages from node V, and this message is a function of the private initial observation of that node and whatever messages it had received up to that time. And this goes on for t rounds. And then at the end of these t rounds, each node computes an estimate based on its private WV and whatever messages it had received during the rounds of the protocol. And we're going to denote the estimate each node computes as z v hat, right? So this is the estimate of z computed by node v. And how we're going to evaluate the performance of protocols? Essentially, we're going to fix an accuracy parameter epsilon and the confidence parameter delta. And we're going to say that this algorithm A, epsilon delta, computes our function if the maximum probability over all the nodes that that node's estimate is off from the true value by more than epsilon in some distortion function d, if this probability is smaller than delta. So no node has more than delta probability of error, where the error is computed on the basis of thresholding the distortion d against some tolerance epsilon.
So Max, I have a couple of maybe simple questions.
Yes.
So first, so how does the block length, like here, the function makes sense for any block length, or?
Well, so the idea is that each round involves one channel use for each of the edge. So the block, there is no quote unquote block length. I mean, block length is sort of implicitly taken into account.
Okay, so you have fixed block, so you're not going to take block length to go to infinity, or okay. And the other question is, do we care about communication here? Because in my mind, if t is the diameter of the graph, then I can send maybe everything to everyone, and I can achieve.
Well, there's still noise, right? I mean,
there's noise. Okay.
There's noise. So diameter of the graph will play a role, actually, as we will see later. So that clearly you cannot beat that. I mean, that's a fundamental limit. But there's going to be additional overhead on top of that.
Okay.
Right. So our goal is to lower bound what we call the epsilon delta computation time, t of epsilon and delta, and t of epsilon and delta is simply the minimum number of rounds such that there exists a t-round algorithm that epsilon delta computes our function. And of course, you know, the whole notion of block length can be taken into account. Here, the idea would be that you essentially trade time for block length. I mean, that's one obvious thing. So essentially what you do is you eliminate feedback that's naturally present in the definition of this algorithm, and you just let all the nodes use, let's say, you know, length t codes. Right, and then at the end of that, everybody just computes, or you can interleave these things.
Okay.
Right, so this definition naturally accounts for both feedback and at block length. Okay, so how are we going to do this? Here's a strategy. The main idea is really to look at cut sets in this graph. Right, so if I partition the nodes, the set of vertices, into two disjoint subsets, S and S complement, I would like to look at the flow of information from the complement of S into S. So the cut set E sub S consists of all the edges that flow from the complement of S into S. So whenever we have E sub S, this always denotes the set of nodes receiving information. And we're going to look at, for each vertex in that set S, we're going to look at the conditional mutual information between the function value z, f of all the w's, and the estimate of that node, the estimate at that node, given the values of the inputs in all the nodes in S. In other words, here's the idea. We'll look at how much node V in the set S reduces its uncertainty about the value of Z if somehow we assume that all the information about the inputs to the function among the nodes in S has already been shared, and we're just waiting for information to arrive from the complement of S. Right, so that's the idea. So if nodes in S can somehow gain perfect knowledge of all the inputs indexed by the nodes in S, how much information do they still need to get in order to pin down the value of the function? And we're going to consider this for all possible choices of S and all possible nodes V in S, right? So this conditional mutual information essentially captures two competing effects. Intuitively, we would reason something like this. Suppose somebody hands us an algorithm that they claim takes t steps, and epsilon delta computes our target function. Well, if this algorithm is worth its salt, right, then this mutual information at each node has to be lower bounded by something, right? There has to be, each node must extract a non-trivial amount of information about the value of the function. And we're not really looking at, here we're ignoring trivial cases like the function only depends on the value of w at v, in which case that node doesn't really need anybody else. But generically, we would look at the case when if this algorithm delivers what it promises, then each node has to extract useful information from this communication. On the other hand, since our communication takes place over capacity-limited channels, over finitely many uses, this mutual information cannot be too large, right? So it's upper bounded by something, and this something is going to be low. And the upper bound will depend on the number of rounds, whereas the lower bound will depend on the claimed accuracy and confidence of our algorithm. And therefore, our computation time t of epsilon delta has to satisfy essentially a collection of inequalities indexed by the subsets of the nodes, where the lower bound on the mutual information, which is independent of t or s, has to be obviously bounded by the upper bound that now will depend on that time. And then we, well, simply solve the system of inequalities, quote unquote, right? I mean, that's if I were to be really sort of hand wavy about it, right? So this is our goal, and of course, what we're hoping for is that this function of time for the upper bounds is monotonically increasing, which makes sense, right? The more rounds you take, the more information you're allowed to push through this network. And if this function is monotonically increasing, then we can simply invert this C2 and get our lower bound, right? So clearly, this is just pushing notation around, pure abstraction. So now everything really hinges on being able to come up with these bounds. So how are we going to do this? So I'm going to describe first the lower bound, and then the upper bound, and then we'll see where that takes us. So for the lower bound, we refer to this as the small ball bound. And the name comes from a fundamental quantity that appears in this bound, which we call the conditional small ball probability. Now this quantity, which we denote here by L, we define it for any subset of the nodes, right? So what it takes in is a vector of input values corresponding to the nodes in that subset S, and it takes the tolerance epsilon, and it simply looks at the following. It says, okay, I'm going to look at the conditional distribution of the value of the function z, given the realization of the inputs for nodes in S. And I'm going to look at essentially all possible values for z. And I'm going to look at the largest conditional probability that the actual function value, given the nodes in S, differs from a fixed value by no more than epsilon in this distortion. So essentially, this small ball probability captures the difficulty of sort of localizing z to average distortion of epsilon given the observations of values in S. So I give you partial knowledge of the inputs to the function. You still don't know the rest of them, so you cannot evaluate the function. But you could localize this function, the value of the function, to a ball of radius epsilon in this distortion. Of course, I'm being really sort of cavalier here with terminology. I didn't say that D has to be a metric, but let's still think about this as a distortion ball, as one does in source coding theory. So with this definition, we can come up with the following lower bound, which we call the small ball bound. And the bound goes like this. If we have an algorithm that is claimed to epsilon delta compute the value Z, then for every subset of the nodes, S, and for every node in that subset, V, the amount of information, the estimate of the function at V contains about the value of the function, given the inputs to the function among all the nodes in S is lower bounded by a quantity that involves 1 minus delta, that's the probability of error, times log of 1 over the expected value of this small ball probability minus the binary entropy of delta. So this is kind of a Fano-like bound. And the proof essentially is more or less like you would proceed in the case of Fano. It goes through change of measure. So we consider the case where Z and Z hat V are connected through the protocol. So they're given the values WS, they are dependent, versus the case where they're conditionally independent given WS, and then perform change of measure. And then, data processing inequality for relative entropy makes an appearance, and then you just push through all the probabilities and look at the event that the value of ZV hat is off by more than epsilon in this distortion, and simply just reduce everything to data processing. You compute the binary divergence between two Bernoulli random variables, right? So that's the idea. Right, so this lower bound essentially holds for any algorithm that epsilon delta computes our function. Right, okay. So let's normally, I would then proceed to upper bounds, but now I actually want to break it up a little bit, and instead of going to upper bounds, let's see what this lower bound actually looks like. So let's look at a concrete example. When let's say our WVs are real valued, and everybody wants to compute a linear combination of these WVs where the coefficients are fixed and known to everybody. So each node has a coefficient A sub V, and everybody wants to compute essentially the inner product of two vectors, right? The inner product of the vector of the coefficients with the vector of inputs. And we're going to assume that the WVs are independent. In this case, the small ball probability can actually be expressed in terms of another quantity, which is well known from probability theory, called the Levy concentration function. And so the Levy concentration function for a real valued random variable U evaluated at rho is essentially the largest probability of an interval of length no more than epsilon situated at any point, right? So the idea is that what we're doing is we're asking what's the probability that U lies between V minus epsilon and V plus epsilon. And then we simply take the soup over all possible values of V. And this quantity essentially captures the spread of the distribution of U. And then a simple calculation actually shows that for the case of this linear function computation, the small ball probability given a subset S is simply equal to the Levy concentration function of only the part of the function that you can't compute because you don't know what's in the complement of S, right? So if you look at this expression right here, I can highlight it. So this is essentially the part of the function. Yes?
So what is the effect of rho in the definition in calligraphic alpha? Role of rho.
Oh, this epsilon is supposed to be rho.
Okay.
Sorry about that. I'm staring at this and it makes perfect sense to me, but of course, yes, rho should be epsilon here. I need to fix that. Thank you for pointing that out. And now everybody, this will be permanently recorded. Oh, well. So here's the idea. The small ball probability for this linear function is actually given by the Levy concentration function of the part of Z that we still are missing, right? Because we're assuming that the WVs are independent. So really, all the nodes in S are just missing this part. right? So only the part of f that depends on knowledge of the inputs in the complement of our set. And we can actually, now that we know this, we can use a lot of known results on these Levy concentration functions in order to say something concrete. For example, let's suppose that the WVs are IID, and they are log concave, right? So essentially, I mean, if you want to have an example, so if each of the W's has a density whose logarithm is a concave function, and you can make this more precise by allowing negative and positive infinity in the log of that. So, for example, Gaussians are log concave, uniform random variables on an interval are log concave, etc. If this happens, then we have a nice bound by Babkov and Chistyakov from 2013 for Levy concentration functions of log concave random variables. And in particular, we can upper bound this Levy concentration function by something that depends on epsilon, and it depends on the variance. So here we're assuming finite second moment. So this is the common variance of the WVs times the norm, squared norm of the vector of the coefficients in the missing part of the function, plus something that depends on epsilon. And this immediately gives us a lower bound on the mutual information that any epsilon delta computing algorithm can extract at each node, right? So we have a nice dependence. Here's our confidence. And notice that this scales at least as fast as log of 1/epsilon. And it makes perfect sense. The more energy there is in the missing coefficients, the larger the computation, the larger the mutual information is, and things like that. So in particular, this bound this lower bound increases, tends to infinity as epsilon goes to 0, which already is an improvement on some of the existing bounds for similar problems that did not have that property. So those bounds would just saturate at some value. Whereas, of course, generally, as you make your computation requirements more stringent, you should be able to require more and more information. Here's another example. So this is the example in the top part is continuous random variables with densities. For the discrete case, we consider, let's say, Rademacher random variables. Those are the ones that take value plus or minus 1 with equal probability. And then it turns out that the computation of concentration functions for these is actually a classic problem, going back to Littlewood and Offord. Tight bounds were derived by Erdős in 1945, and essentially they involve a lot of combinatorics, obviously. I mean, it's simple counting, but then we can use Stirling's approximation to express it as essentially something that scales as 1 over the square root of the number of nodes in the complement of S. And this tells us that the amount of information that has to arrive about the function to each node through the nodes in S complement is lower bounded by the log cardinality of that S complement. And we'll see examples of this later. Okay, so these are some of the examples. So this shows you that this small ball based lower bound is actually useful in some sense. All right, next, let's look at upper bounds. And here we have two options. One is the obvious thing, just look at the cutset capacity, right? So split the set of vertices into two subsets, S and S complement, and look at the total capacity of channels that communicate information from S complement to S. So it's obvious that, more or less obvious, but some work needs to be done, that if A is a T-round algorithm, then for any subset of the nodes and any vertex in that subset, the amount of information that that node will receive about the function value given total sharing of inputs among the nodes in S is upper bounded by essentially two things. Either the number of rounds times the capacity of of all the channels traversing the cut, or the conditional entropy of the function value given the inputs in S. Obviously, that conditional entropy bound is only meaningful when it exists. But since the channels are assumed to be finite capacity, this upper bound is always finite. So you can see the graph here gives us the cutset bound. So essentially, we have a line of slope given by the cutset capacity. So the sum of the capacities of all the channels traversing the cut in the direction from S complement to S, so into S, and a straight line corresponding to this conditional entropy, if that conditional entropy is finite. So that's one obvious upper bound. The other upper bound is more refined and is based on strong data processing inequalities, right? So by now, I think everybody knows what strong data processing inequalities are. But just in case, suppose I have a channel K that maps a random variable X into another random variable Y. So what I do is I look at the ratio of the relative entropies between two output distributions induced by two input distributions. And I simply look at the worst case such ratio. By data processing, we know it's less than or equal to 1, right? But as first shown in a remarkable paper by Alsvedi and Gach in 1976, in many cases, this ratio is actually strictly smaller than 1, which essentially says that this channel is noisy. It dissipates information as you send inputs through it. An equivalent formulation of strong data processing is if I look at the situation where I wish to communicate some random quantity U by coding it into an input for this channel. And I look at the ratio of mutual information between U and the output of the channel to the mutual information between U and the input of the channel. So you can think about sort of mutual information between U and X is, think about it as the sort of rate in a way, right? And this is how much information how you compress U into X. And then you look at how much information you receive, you look at the ratio, and it can be shown that this formulation of strong data processing is equivalent to the original one. And again, this was in the original paper by Alsvedi and Gach, but also used by Evans and Schulman in 1999 in the context of reliable computation by Boolean circuits with noisy gates, and later was taken up by Anantharam et al. In the context of hypercontractivity estimates. And in some cases, you can actually compute these things exactly. For example, if I have a binary symmetric channel with crossover probability epsilon, its strong data processing constant is equal to 1 minus 2 epsilon squared. And if I have an erasure channel with erasure probability epsilon, strong data processing constant is exactly 1 minus epsilon. So where does that leave us? There's a very useful result that if I have a collection of channels, suppose I have a collection of channels and I'm allowed to use them in parallel. So what happens here is I have M channels and I'm allowed to code the inputs to that channel jointly. So in other words, this tensor product notation basically says that the input will now be a vector of inputs, right? X, one for each of the channels. And the output is also similarly a vector. So what I'm doing is I'm sending information through a parallel collection of channels. And that can be shown that this parallel collection has a strong data processing constant. And a strong data processing constant can be upper bounded by a quantity involving the sort of largest eta among all these constituent channels. As you can see, this quantity, the upper bound converges to 1 when the number of channels goes to infinity, for example, which is useful, right? So the more information, the more parallel channels you use, the more informative you can be. And the first bound of this sort for binary inputs and binary symmetric channels is due to Evans and Schulman in that paper about noisy Boolean circuits. And then Polyansky and Wu generalizes to a great extent, in particular allowing even noiseless feedback. right? And the proof is fairly simple. It's by backward induction and by chain rule for the mutual information. All right. So here's the idea. Here's another upper bound on this mutual information using strong data processing inequality. So let's look at a particular node V, and let's look at all the channels that can send information to that node, right? So E sub V is a set of edges starting somewhere else on the network, but ending up at node V. And let's look at the, so each of these edges comes with a channel, right? So what we want to do is we want to look at the largest strong data processing constant for all these channels. And obviously this is less than or equal to 1. And then a simple application of the previous lemma, and essentially chain rule and related things recursively, gives us the following bound. So if we have a T-round algorithm and any subset of nodes S and any node in that set S, then the mutual information, conditional mutual information between the value of the function and the node's estimate, given all the inputs in set S, is upper bounded by a quantity that involves this sort of least noisy channel sending information to that node V, and we raise it to the number of edges in that that impinge on V times the number of rounds times this conditional entropy. So this is uncertainty about the remaining inputs of the function, given that all the inputs in S have been shared, right? So now we can combine these and get an upper bound on the mutual information, combining that with the lower bound through the small ball probability, we get lower bounds on the epsilon delta computation time. We have to apologize. I have to apologize for this. I just keep coughing because I'm recovering from a cold, but somehow, you know, for weeks and weeks, your voice can still sort of give up on you at the most important times. Right. So what I want to emphasize is that the lower bound only takes into account that what we have is an algorithm that takes however many rounds it takes, but delivers a certain accuracy and certain confidence. Right. And this is the L of S, epsilon, and delta. And the upper bound, in turn, depends only on the fact that we are communicating over a network. The edges are equipped with channels of finite capacity, and the number of communication rounds is bounded by T. And then you can crank through the bounds and get these estimates, right? So let's see how this manifests itself. A very simple example, because if you can't really handle such a simple example, then it's not interesting. So what we have is just two nodes. Each of them has a bit. So each node has an equiprobable bit, independent. And the two nodes want to just compute their XOR, the mod 2 sum. So we can come up with two bounds on the computation time, one based on cutset capacity, and that's this one. And the other one is based on SDPI. So here what happens is we fix, so if we want to compute it up to tolerance P, this is this is a dependence of the bounds on computation time, like the upper bounds on the computation time. So you can see that at some point the cutset capacity bound becomes worse than the bound based on strong data processing inequalities. And all of these bounds can be achieved. So for example, you can achieve the SDPI bound simply by more or less repetition coding. And just, and then a large deviation estimate gives you a probability of error, or you can achieve the cutset bound by random coding because you actually want to hit the capacity. right? So this actually goes back to the question about block length. So, you know, essentially the cut set bound is more or less implicitly talking about trading block length for accuracy, right? Okay, I assume I'm still live, right?
Yes, yes.
Okay, yeah, because everybody's silent.
Yeah, we just mute ourselves so we don't make noise.
Okay, good. All right. So so all of this is good and well. Here's another example. This is a more complicated thing. So this is a barbell network. So essentially you have two cliques of equal size that are connected by a single edge, bidirectional edge. And, you know, and so graphs like this illustrate various bottlenecks. So here we have two cliques that everybody talks to everybody else, but then the bottleneck is these two nodes that have to exchange information between these two cliques. So here the idea is that the inputs to the nodes are IID Rademacher, right? So equal probable plus or minus 1, independent. All the channels are binary symmetric channels with the same crossover probability, and you want to compute this sum of these plus or minus ones. Lower bound is using this Littlewood offered estimate, the small ball probability. So essentially it's big omega of log of the number of vertices. So let's see if we can achieve it. Well, it turns out you can. And this uses kind of an idea from a paper by Bob Gallagher about computing parity in a broadcast network, so in each of the cliques, where there's noise on the channel between any two pair of nodes. So he was talking about computing parity, but you can easily convert this into computing sums of plus or minus 1 random variables. And the idea is to essentially split the set of nodes into non-overlapping sets in just the right way, and use something like median estimators to exchange information. So the idea is that we can estimate the partial sum over each of the cliques for each node in about log V rounds, right? V is the cardinality of the network. Like each clique is half the network, right? So that's Gallagher's protocol. And then what happens is that once every node in each clique knows the partial sum, the two nodes that are responsible for talking to each other can essentially communicate this partial sum using log V rounds, right? Because we know how many values this partial sum can take, and they just exchange this value. And then what happens?
Question.
Yes.
Does it make sense here to compare it to? I mean, I'm thinking, like I'm doing like a separation-based solution, like gossip plus coding, like coding to get rid of noise and then do gossip. Does it apply to this setting?
Possibly. Although in this case there's this whole issue of I mean, effectively that's what it is. But
so that's optimal. So that would be
that's optimal, right? I mean, effectively this is what this ends up doing, right? I mean, so the two cliques compute their parity, and I mean, you could probably do it less efficiently, but Gallagher's protocol is just very nice. The point is that the communication is bounded really by the effort it takes for the two representatives of the two cliques to exchange their corresponding partial sums, and then the two nodes just spread that information around.
Yeah.
I have a quick question.
Yeah.
So, you know by any chance how the number of rounds also scales with delta? Delta captures the quality, right?
Yeah. Well, so the lower bound it's 1 minus delta, plus the usual binary entropy. In the upper bound, we didn't really account for that. I think here we're actually interested in, let's say, delta is something like a fixed number. I mean, it's still an interesting question how the upper bound scales with delta, but in this case, we didn't work it out. and this work is a few years old. I still remember most of the details, but not that particular calculation, which we may have done, but you know. But the point is that as far as the dependence on the number of nodes goes, this is tight, right? Because both the lower and the upper bounds are log of the number of vertices. Okay. All right. And this, by the way, also accords with this notion of graph diameter, because this graph has, you know, the diameter of this graph is essentially a constant. It's 3. Right, because you have the 1 between the two nodes that connected to cliques, and then 1 distance of 1 from that node to all the other nodes in the clique. So clearly, the fact that this does not scale linearly with the number of nodes is a good indication of the tightness. Okay. So on the other hand, so this cut set analysis is kind of limited, right? Because it accounts for this information flow across the cut set, right? But the thing is that it assumes somehow that the difficulty comes from the fact that, well, these nodes in S, they still need information about the inputs to the function that the nodes in the complementary set have. But on the other hand, once this information traverses the cut set, it has to actually spread through the rest of S. So we need to account for that as well. And so we can actually do this using multiple cuts, as I will show now. And this analysis will actually bring out the dependence on the network diameter, as one would expect. Okay, so let's see. First, illustrate this for a simpler case, where the network is actually a bidirectional chain. So the information essentially can flow from left to right and from right to left, but only from node to node. So essentially, each node can only communicate with its neighbors to the left and to the right. So if I were to have such an n-node chain of bidirected links, and I fix the maximum strong data processing constant on each of these channels, then I can upper bound. So the lower bound using small ball probabilities is still in force. What I care about is the upper bound. So now, if I have a T-round algorithm, I can actually upper bound. Let's say I look at the cut where I'm looking at how the information spreads between nodes 2, 3, and 4. Here in this network, you see node 1 has to send information about its input to node 2, and then node 2 has to propagate that information to 3 and 4. So we're looking at this from the viewpoint of nodes 2, 3, and 4. Right? So here the idea is that we can get these upper bounds that depend on essentially the uncertainty about W1 given all the nodes in the network times all this other stuff, right? So these are the data processing constants: number of rounds, number of nodes. And once you, so these are the two bounds. So one of them is a cut set bound, and the other one is essentially a combination of strong data processing bounds. And then when we invert them to get the time, right? Because time appears here in both cases. Well, here it appears both multiplying t, right? Multiplying this t minus n plus 2, and here it appears as an exponent in the data processing constant. If we invert these, we get a cut set bound, and we get an SDPI bound. And the interesting thing here is that n minus 2, so n here is the diameter of this network. So it actually appears explicitly in both bounds. And whatever else we have on top of that is due to the fact that there's noise and you have to correct for it. And the analysis is essentially based on representing the space-time graph of the computation, kind of chasing all the conditional independence relations in it. There's a lot of chain rule for mutual information and careful application of cut set and SDPI bounds. Right. So so let's just I mean it looks like an awful type of awful looking formula. I've been talking for 47 minutes, but I think we have time. But let's unpack what this means. So remember that we still have the small ball lower bound that holds for any algorithm that claims to deliver accuracy epsilon and confidence delta. So lower bound on the amount of information extracted by the algorithm. And the lower bound on the time that such an algorithm would take has two terms. Essentially, it has the diameter of the network, and that would be present even if there were no noise, because this information has to flow from the leftmost node to the rightmost node and the other way. But then we also have effective noise and uncertainty, right? So here we see that, for example, this is a small ball probability for epsilon delta computing, given that information from node 1 is missing, divided by the entropy of W1 given all the rest, etc. And the proof, like I said, so here the idea is that even in this simple network, the relation between all the random variables exchanged during the protocol is fairly complicated. But because of the local structure of the graph, it has all sorts of conditional independence relations. And we simply exploit them, using a lot of Bayesian network reduction techniques, conditional independence relations and things like that, and then just recursively apply cutset and or SDPI bounds. And essentially this, one way to think about it is an extension of Rajagopalan and Schulman's result. And they were interested in propagating a bit through a chain of binary symmetric channels. Recently, there was some work from Yuri Polyansky's group, I think at ISIT this summer, where they got much more refined bounds on this. But so this theorem applies to a bidirected chain. So for an arbitrary network, and I want to make this really short, what you can do is essentially reduce it to a bidirected chain where each of the nodes also has self loops. And roughly speaking, the idea is something like this. What you want to do is you want to partition the set of vertices into disjoint subsets in such a way that the cut sets between the neighboring sets are disjoint. So in other words, if I have subsets Si and Si plus 1, then information flowing from Si to Si minus 1 and from Si to Si plus 1, these edges are sets of edges are disjoint. And you can actually always choose these subsets in such a way that the number of subsets that you partition the vertices into is equal to 1 minus the diameter of the graph. And the idea is essentially to kind of fix one node, look at all the nodes within one hop, within 2 hops, etc. So so this gives you concentric sort of spheres in the graph distance, and then just partition things in that way. And the idea is that once I do this, I can essentially simulate the protocol running on the original network by a protocol running on this bidirected chain. So here the idea is that what we do is we lump all the vertices in each of the subsets into a super vertex. And this 1 prime, 2 prime, 3 prime, 4 prime, 5 prime, you can think about partitioning using these cuts into 5 subsets. And each of the subsets is represented by a supernode. So the 2 links going from one supernode to the other represent the channels traversing the cuts. And then the self loops correspond to computation within each of the sets, or communication within each of the sets. And the idea is that if I have an algorithm that runs on the original graph, by this reduction, just by mapping channels appropriately, mapping edges and and things like that, you can simulate it by an algorithm A prime running on this reduced algorithm. And then, of course, we know that therefore the lower bound for any algorithm on the original graph has to be larger than the lower bound for the new graph, right?
Can you optimize on this kind of concentric cuts?
I'm sorry?
Or could you optimize? Does it make sense how you make these cuts? Because there's not a unique way to do it.
It's not unique. No, if I remember correctly, there's no, it doesn't really matter.
Okay.
As long as you just fix one node and then you kind of go out in these concentric spheres.
Okay.
Okay, so if you do that, then we can immediately apply the previous theorem, this one, for a bidirectional chain. That gives us a lower bound for the original network. So obviously this bound would depend on the successive partition, but the main thing is that what is nice is that this accounts for the diameter through this term, and it accounts for number of nodes, and it accounts for sort of the maximum density of connections. So this delta looks at the largest, essentially maximum number of all these subsets. How many edges go in, how many edges go out, and how many edges sort of circulate information within each set. Right, and then the nice thing is that if we insist on both epsilon and delta to exponentially decay the number of nodes, then the number of then the communication time is going to be lower bounded by n, which is essentially diameter, divided by delta. So the denser the connections are, the less time you would need, and divided by eta. So the noisier the channels, the more time you would need. And and here. The idea is that really everything hinges on this maximum sort of density of connections, and you can compute it for various topologies. For example, if we have a ring, then the rings are not very dense. Here's an example of a successive partitioning of a ring graph. And here we assume bidirectional edges. So that's why they're drawn without errors, without arrows, not errors. Hopefully they're drawn without errors. So this density of connections is actually a constant for the ring. For a d-regular tree, as you would expect, it's equal to d, right? Number of edges that each node talks to. And for grids, if we have a grid roughly n by n, then this maximum connectivity is upper bounded by n. So that's and you can partition the grids in this way. So each of them has an example of how you would partition this. Okay, so I think I've talked enough. This paper, as I said, from 3 years ago, something I'm still very happy about, because this was sort of the first project that Aolin started working on, and it took a couple of false starts before we really zeroed in on some of the right connections. In particular, this idea of multiple cuts was a very unexpected and very cool construction that he came up with. And this was published in the Transactions. But then, if you want to look at it right now and you don't have the access to your IEEE Explorer, you can go and click on this archive link, and everything is there. So thank you.